The sun's surface blazes at 5,500 degrees C, but its corona, the wispy outer atmosphere, reaches millions of degrees. That's like a campfire that gets hotter the farther you stand from it. For 80 years, this coronal heating problem has defied explanation. This is still unexplained, the science that hasn't finished arguing. But here's the twist. Parker Solar Probe flew through this inferno and found magnetic switchbacks everywhere. Instead of solving the mystery, it deepened it. How could the outer atmosphere be hotter than the fire beneath it? The puzzle emerged in the 1940s. Astronomers spotted spectral lines from gas at millions of degrees, yet the visible surface below is just 500 degrees Celsius. Two main theories battle for dominance: Alfven waves, which ripple along magnetic fields, and nanoflares, tiny explosions from magnetic reconnection. Which one truly heats the corona? What actually heats the corona? Churning plasma twists magnetic fields into loops. When these snap, they release nanoflares, or Alfven waves ripple upward, carrying energy. Both ideas are plausible. Both may be at work. Nanoflares come from magnetic reconnection. Lab experiments have recreated them from braided loops, confirming the mechanism is real. Alfven waves are torsional vibrations along flux tubes, carrying energy from surface to corona. They're highly regarded as the carrier. But which dominates? To settle the debate, NASA launched Parker Solar Probe in 2018. It's the fastest object ever built, hurtling through the corona at 430,000 mph, enduring 1,400 degrees, all to sample the solar wind at its source. In December 2021, it crossed the Alfvén critical surface, the boundary where the sun's magnetic field loses grip. For the first time, a spacecraft was inside the corona. In 2019, it found switchbacks, plentiful near the sun. Their origin? Magnetic funnels between supergranules. Suddenly, they were a clue. Switchbacks are nonlinear Alfven waves tied to global magnetic circulation. They could carry energy, but are they the cause or a symptom? But the probe's data revealed a new piece that fits no model. As one researcher admitted, we're missing something fundamental about the sun. The mystery just got deeper. Could both mechanisms be at work? The data suggests they are intertwined. Reconnection can launch Alfven waves, which heat surrounding plasma. The sun is more complex. But here's the catch. The energy budget still isn't apportioned. As of 2026, the problem remains unsolved. The sun keeps its secret. The energy budget remains unapportioned. As of 2026, no single mechanism has claimed the crown. The question sharpens. Will we ever know? But perhaps the search itself is the wonder. Each mission peels back a layer, and the mystery persists. That's what keeps us looking. Parker keeps flying, and new missions like Solar Orbiter join the hunt. Each orbit brings us closer to an answer. But where do switchbacks come from? Parker's data traced them to magnetic funnels at the sun's surface, nestled between supergranules. These funnels act like chimneys, funneling energy upward. Yet their exact role in heating remains a puzzle, hinting at a deeper connection between surface activity and coronal temperatures. So which is it? Waves or explosions? Alfven waves ripple along magnetic field lines, carrying energy from the surface. Nanoflares are tiny explosions from magnetic reconnection. Both have been observed, but their relative contribution to coronal heating is still debated. Some scientists think they work together, each playing a role in the complex energy transfer. But not all Alfven waves are equal. Kinetic Alfven waves, with slightly higher perpendicular wave numbers, are more efficient at transporting energy along flux tubes. They move faster and carry more punch. This refinement suggests that wave heating might be more effective than previously thought, adding another layer to the puzzle. Nanoflares can be tested. In laboratories, scientists have recreated them by braiding plasma loops. When these loops snap, they release energy in bursts. These experiments confirm that nanoflares are real and could contribute to coronal heating. But scaling these lab results to the Sun's vast corona remains a challenge. The core issue is the energy budget. How much energy do waves carry? How much do nanoflares release? Parker's data shows both are present, but neither accounts for the full heating. There's a gap, a missing piece. This gap suggests that our models are incomplete and something else might be at play. Switchbacks are not just curiosities, they might be energy carriers. As non-linear Alfven waves, they could transport significant energy from the Sun's surface to the corona. If so, they could be a major piece of the puzzle, but their exact role is still unclear. The Sun's surface is covered with supergranules, large convection cells. Between them, magnetic funnels emerge, acting as conduits for energy. These funnels are where switchbacks are born. Understanding this magnetic carpet is crucial to solving the coronal heating problem. Parker's solar probe isn't done yet. It continues to dive closer to the Sun, making multiple passes through the corona. Each orbit brings it nearer, sampling the solar wind at unprecedented distances. These close encounters provide data that no other mission can, and they're essential for testing theories of coronal heating. But Parker isn't alone. Solar Orbiter, a joint mission with ESA, is also studying the Sun from a different angle. It captures high-resolution images of the corona and measures the solar wind. Together, these missions provide complementary data, helping scientists piece together the puzzle of coronal heating. After 80 years, the coronal heating problem remains unsolved. Despite decades of observations and theories, no single mechanism has been proven. The Sun's corona is a complex system. Our understanding is still incomplete, but each mission brings us closer. Future missions and advanced computer models will refine our understanding. Scientists are developing more detailed simulations that incorporate both waves and nanoflares. New instruments will measure the corona with greater precision. The answer may be a combination of mechanisms, but we're not there yet. That's the beauty of science, a journey without a final destination. Every answer reveals new questions. Subscribe to keep exploring the mysteries of our universe. Some questions still don't have an ending. Subscribe for the next one. Up next, nothing about sperm whales is normal.